All right, let's dig in. Today we're looking at something pretty amazing, a really simple but super powerful way to check the health of the ground right under our feet. Yep, we're talking about soil. We're going to see how scientists use just a simple metal cylinder to figure out its whole story. So let's get right to it.
It sounds like a weird question, right? Can the ground get tired, overworked, exhausted, even damaged? Well, the short answer is a big yes. And when it does, it really struggles to support all the life that depends on it.
So, picture this. On one side, you've got healthy soil. Think of a brand new kitchen sponge. It's fluffy, it's porous, full of all these little gaps and channels that can hold air and water. It lets roots just spread out and grow. But on the other side, you've got compacted soil, and that's like a rock. It's dense, it's hard, it's suffocating, really. All those spaces that give soil life have just been squeezed shut. Now, what's really wild is the history here. For pretty much all of human history, farming and tilling actually helped the soil. It loosened everything up, made it more porous. But today, with these massive, heavy tractors and combines, well, that's completely flipped the script. All that weight can cause intense compaction, which is a huge deal when it comes to soil health.
Okay, so how do we actually measure this compaction problem? Well, scientists have this one key indicator, kind of like a secret number that tells them exactly how tightly packed a soil is, and it's called bulk density.
The idea behind it is actually beautiful in its simplicity. Bulk density is just the mass of the dry soil divided by the space it takes up. Let's go back to that sponge. A fluffy, dry sponge is super light for its size, right? So it has a low bulk density. But now, what if you squish that sponge down into a tiny, hard little cube? It has the exact same weight, but it takes up way less space. That means its bulk density is suddenly much, much higher. And that perfectly illustrates what soil's made of. You've got the solid bits, the minerals, the organic matter. But what's just as important, if not more so, is the empty space, the pores. That's where the air and water live, which is absolutely essential for life. So bulk density is really just a way to measure the ratio between those solid particles and that vital empty space. And look, you don't have to take my word for it. The Food and Agricultural Organization of the United Nations, which is our source for this explainer, they put it really plainly. This one measurement is a direct indicator of both soil compaction and its overall health. Full stop. So how do they actually get this number? Let's head out into the field and see how it's done. I like to think of the scientists doing this as soil doctors, out there doing a checkup, and their most important tool, a simple metal cylinder. And here's the kit. It's pretty low tech, which is kind of cool. You've got your stainless steel cylinder, which has a very specific known volume, a holder and a hammer to get it into the ground, a knife and brush for trimming, and of course, some bags and a marker to label everything. The process itself is really careful and methodical. First, they clear a little patch of ground. Then, that cylinder is gently hammered in until the top of it is perfectly level with the soil surface. Now here's the crucial part. To get it out, they don't just pull it. They dig around the cylinder. Why? To make sure that core of soil inside stays perfectly undisturbed. Finally, they just trim any excess soil off the top and bottom, cap it, and seal it up for the trip to the lab. Okay, so with that perfect little sample, it's off to the lab. This is where that cylinder of dirt is going to get turned into some hard data. The lab work really just comes down to 3 key steps. First, they weigh the fresh, moist sample exactly as it came from the field. Then, it goes into a special oven set to 105 degrees Celsius for a full 24 hours. This bakes out every single last drop of water. After it cools down, it gets weighed one last time. And that final weight, that's the pure, dry mass of just the soil particles. And here's where it all comes together. You now have the dry mass of the soil, and you already knew the precise volume of the cylinder it came in. So the calculation couldn't be simpler. You just divide the mass by the volume. And boom, that's your bulk density number. Okay, great. So we have a number. But what does that number actually tell us? Let's take a look at how to read these results and figure out what they mean for the plants trying to survive in that soil. You can basically think of this as a report card for the soil. Now, what's really interesting here is that a good or bad number totally depends on the soil's texture. So for a nice loamy soil, anything under 1.4 grams per cubic centimeter is great. But for a really heavy clay soil, the ideal number is way lower, under 1.1. And that's just because those tiny clay particles can naturally pack together much more tightly. Let's just focus on that loam soil to make this super clear. See the green zone, under 1.4? That's your happy place. Roots are having a great time. But as you start to creep up, say to around 1.6, you can see root growth starts to suffer. And then once you cross into that red zone, above 1.8, you've got a serious problem. The soil is literally so dense, it's physically stopping roots from growing. And at the absolute extreme end, the data shows that once you get over about 1.89 grams per cubic centimeter, forget about it. Plant roots can hardly penetrate the soil at all. The ground has basically become a brick wall, just blocking off access to water and nutrients. So why does all of this matter so much? Because we can actually do something about it. We can reduce the risk of compaction. Things like using cover crops to protect the soil, having designated paths for heavy equipment, adding more organic matter, and disturbing the soil as little as possible. All these things can help keep that healthy, spongy structure we talked about at the beginning. And that kind of brings us to our final thought here. The next time you're walking across a field or through a park, or even just in your own backyard, think about this for a second. Does the ground feel a little springy and alive under your feet, or is it hard as a rock? Now that you know how to read the signs, what story is the soil in your world telling you?